And as Janine said, feel free to ask a question during the talk if you have one. First, I'm going to go over, and the talk in general is largely an overview. I'm going to go over first the current state of fire modeling, and before that even just a general overview of modeling and overall, and then some examples of limitations of current fire spread models, and then examples of physics-based modeling for fire behavior. And then for any model, you need measurements in order to know how well the model is working. And I'll discuss very briefly what would be good to have in terms of measurements as we move forward. So first, because fire behavior is a collection of a lot of processes going on, and to really understand any physical behavior, you really need to know something about the processes. I have this slide so that we're all on the same page as we go through the presentation, and I make some references to some of these processes. So this is just a snapshot of a fire, and I'm showing from the bottom of the fire upwards that you have the process of drying and thermal degradation, or basically burning of the vegetation. And then as you go upward, you have combustion of the resulting fuel gases as they mix with oxygen and the creation of smoke. And then finally, as you go to the highest point on this graph, you have plume rise and smoke transport. And fundamental to all of the things happening, especially in the bottom two, are heat fluxes. Those are the driving components that result in the drying and the transfer of heat from combustion that gives rise to the plume movement, whether fire or smoke plume. So any advances, at least in my opinion, in modeling should consider heat fluxes and, in more general, fire brand fluxes or ember fluxes. If you go to wildland-urban interface fires, as shown on this picture, you have all of the problems or challenges that the wildland fire presents in terms of modeling. And you can see this is a picture of a fire in wildland fuels approaching a community. Now it's heading into the wind, so it's a backing fire, and this community in particular was not damaged by this fire because of that. But if it had spread into the community, you can see that you still have vegetative fuels, but you have all of these structural fuels in addition. And so a wildland-urban interface fire in general has all the complexities and challenges of a wildland fire and the complexities that are presented by the urban environment or the built environment. You have the additional fuels, structural fuels. You have very discontinuous fuels. They're discontinuous in space. They're discontinuous in type. And so it's a more challenging problem, actually. And in some ways, you're going from a fire spread problem to into a fire ignition problem when you're talking about the structures. So in general, and this is very much in general, because I'm not considering statistical models here, there's two types of models. Those that are explicitly account for the driving physical processes. And by those, I call those physics-based models here. And then there's a group of models that do not explicitly account for the physical processes. And those I'm calling empirical or rule-based. And so the second group of models is concerned more with the outcome of all the physical processes, like a measure of the spread rate, but not necessarily the processes that result in that spread rate. As a very general example between of these two groups of models, I'm showing two photos here. On the left, you have Orville and Wilbur Wright on the morning of their famous launch, doing something. It didn't say in the captions of the figures when I found this, but it looks like they're measuring the wind. And this is, they're not connecting that wind speed to anything having to do with the processes of flight or the mechanics of flight. This is a kind of a rule of thumb check before they take off. On the right picture, you have the Apollo launch some 65 years later. And that kind of endeavor required a lot more knowledge of the physical processes because, for example, you're heading out into environments that are not directly observable out in space and around the moon. So you need to have some knowledge of the processes across a range of environmental conditions when you went to the moon, as compared to when they first launched their first flight. Because so the scope, and like I say in the bottom here, all of these approaches are useful. What you want to do depends on the scope, or which you want to use depends on the scope of the problem and the needs of the user. For the Wright brothers, they didn't have to fly very high off the ground or go very far compared to the Apollo launch. Now, physics-based models can be a combination of models, and it's impossible to actually solve all the physical, I guess you call conservation equations for all the physical processes from the scale of ignition of a fire all the way up to, say, this smoke transport picture you see here. So a modeler that's using physics-based approaches needs to choose basically their scale of operation. So someone that's focused on atmospheric processes, it's like smoke plume transport, has to resolve things in the order of tens of kilometers. That means there's no way they're going to resolve the fire. And so that has to be essentially heavily approximated or dumbed down. So in this talk, I'm not going to be focused on these scales. I'm going to be focused more on the scales near to the fire, or the order of the size of the fire itself. I'm going to spend there's a couple slides here just going over examples, and I'll go into more specific examples and with graphs and that kind of, and some figures and images later. But there's two slides here on the limitations of these kinds of models. For empirical models, strictly speaking, you should not use the model under in environmental conditions that are not that the experiments or measurements that were used to derive the model did not cover. So, for example, a model developed for the rate of spread in grass should not be used to predict the rate of spread in litter, trees, or potentially even other grass fuels. Secondly, when these measurements are made, for example, in the laboratory, there may be the experiments may have been done in a certain way that limits their applicability to the field. For example, a wind tunnel is confined. It has walls and ceilings which don't exist in the field. Secondly, and this is the first example I listed here, when you do measurements in the lab, you try to idealize situations to some degree so that you can control things. And one example would be to do measurements of fire spread in the lab for fires that are spreading at a steady rate. So you would be ignoring the initial phase after ignition that may have some acceleration in the spread rate, and look only at later times when it's quasi-steady spread rate. And the question is that really, how applicable is that to real scenarios? For physics-based models, and these are just examples. I mean, there's obviously a large number of these issues. There's errors due to model approximations. Like I mentioned with the image above before, any approximation that's used for the fire here is going to result in some kind of errors. So the example I have here listed first is that we assume in these physics-based models that the only way that live fuels and dead fuels are distinguished from each other is by their moisture content, live fuels in general having a higher moisture content. Second example is that the models for the actual burning of the vegetation are based on laboratory measurements that are often, pretty much always, not at the same heat flux conditions that the vegetation would be subjected to in a large fire in the field. The heat fluxes are smaller, basically. Finally, in the numerical solution of the equations, you have what are called discretization errors because you're solving those equations on a computational grid. Now, both the limitations in both these types of model are always going to be there. What needs to be done is that they need to be characterized. So, for example, how important is the assumption that live fuel and dead fuels differ only by their moisture content? That's an approximation that has to be made at this point because we don't have any better information from measurements. But the real question is, well, what happens when you apply this model, this approach, this approximation to live fuels? Is this approximation really causing you problems or not? So characterizing the impact of these limitations is really where modeling effort, a significant amount of modeling effort should be put in, but often it's not. So today, in the Forest Service, the fire spread models used are they're empirically based, mostly Ruddy Mell equation, and they are the engine driving a lot of other tools out there, which I've listed. The processes, the physical processes, are not modeled explicitly. The major model assumption is that the spread rate is constant. And this was done because it really made it possible in the laboratory to get something out of the experiments that could be used. And it meant that in the laboratory, the wind was held constant, the fuel type was held constant, and the slope was held constant. So it was not possible under this assumption to account for changes in the spread rate due to going from one fuel type to another. If you apply this kind of model, you assume that spread rate change due to the change in the fuel happens instantaneously, or you have a fudge factor in there, which is not based on any measurements. Now, the Ruddy Mell model was obviously developed a long time ago in a different era, when problems associated with fire like smoke, fire effects, and structure ignition were not as important. Also, computational capability was much more limited. So the model was designed to address problems that are not necessarily the most important problems today and cannot provide the information, therefore, that is needed to address these problems. In addition, this model is, work on the model was started in the early 60s. So this model is about 50 years old, or at least the work that was behind it. And the subsequent advances in computational capabilities have not been used to improve the model itself. They've been used in different ways to deliver the model results, but not to improve the model itself. So I'm going to give some specific examples of the limitations of, in particular, the Ruddy Mell model as implemented in Behave Plus. And again, as I mentioned before, what needs to be done is to characterize how important these limitations are for a given application. I mean, we all know that models have errors. The important thing to know is how relevant are the errors for your application. So we're still beginning to work on that, but this gives you some examples of in what specific scenarios we are considering the errors. So what I have here on the left is the time history of wind speed. And that's in meters per second. And for those of you who are more familiar with miles per hour, basically multiply the meters per second by 2. So this time history of wind speed was put into 3 different models to see what the spread rates would be as a result of these wind speeds. And that's shown in the right-hand image. And if you look at the middle graph in the right-hand image, if you look at the middle box and whisker plot, that is the spread rate prediction from the empirical model developed from the experiments associated with this wind speed. There were a number of experiments done in Australia, grassland fuels, and an empirical relation was developed, and that's what's used here because that's where this wind speed came from. And you see that you have a spread rate of around 1 meter per second with some spread of values around that because you have the different wind speeds. If you go to the right, you see results from what's called WFDS, which is a physics-based model that I'll talk about in a bit. And you see that its average wind spread rate prediction agrees pretty well with the empirical relation from Cheney et al. And there's again some spread around that. If you go to the far left, you have the result from Behave, and you see a significant increase in the spread of the the range of spread rates predicted. You also see that the median, which is shown as that dark line, is significantly higher than the median predicted by the empirical model designed from these experiments. So it's in a large amount of error in its median prediction, and it's also very sensitive to the wind speed. The reason this is happening is that Behave was not developed for these types of grass fuels. And so it's very sensitive to the wind speed as a result, and it's also in error. Now, a user of Behave would not know this if they didn't have any other information. So this is an example of where if testing was done against, obviously here you had the measurement information, and you would find out that the model doesn't work well in these conditions, that information needs to be provided to the user as an example of model limitation. The reason that if you look at the Cheney et al. And the WFDS results, they are not as sensitive to the wind speed because the Cheney et al. Relation depends only on the wind speed. Behave is more the wind speed squared, and WFDS, you don't have a relation like a formula, but it's able to handle, obviously, the processes in a way that are very similar to the empirical relation result. The thing that, I'll just leave it at that for now. So what I'm showing here is an example of the limitations that can occur in the laboratory because of the configuration of the experiment. On the top row here of images, you're seeing fire spreading down a wind tunnel. And then to the right of that, you're looking at the upwind end of the wind tunnel. So you're looking downwind at the fire. The images below, the row of images below, are the wind tunnel, but with half the cross-section dimension. So the wind tunnel on the top is 6 meters by 6 meters across, and then the bottom 3 meters by 3 meters. And what happens is that the bottom wind tunnel is sufficiently small that it confines the fire and smoke plume, which you can see on the picture on the bottom, right bottom corner. You can see the smoke taking up a lot of volume in the upper part of the domain, and that forces the flow down towards the bottom of the domain so that this wind speed near the fire is actually larger than it is for the case above in the larger wind tunnel. So just that confinement effect in the experimental scenario or configuration is changing the spread rate. And it would not be possible to know this unless you had done a lot of measurements. Or you could use a model like this and check things out. In fact, these physics-based models are used very commonly in the engineering community to design and test experiments. This next example is for a fire spreading up a drainage. So I'm showing on the left a drainage, and the water line of that drainage is 600 meters long. The slope is 27 degrees. If you start a fire, and this is where you have grass fuel, where you see green, and where brown or kind of an orangish in the bottom, there's no fuel. If you start a fire along a line shown at the bottom left, and let it head up the drainage, and the winds here are 1 meter per second ambient winds. Under these light winds, the fire-induced wind is sufficiently relevant that it causes the acceleration up the drainage. If the ambient winds were higher, and I'm not showing this, but the model shows this, and other models have shown this, say 5 meters per second, you do not see this kind of acceleration because the contribution from the fire-induced winds is relatively small compared to the ambient wind. So on the right, I'm showing a time history of the heat release rate. That's the heat in kilowatts released by the entire fire. And if the fire reached a spread rate that was steady and the fire line did not increase in length, which it can't happen here because it's confined by this unburned or non-burnable fuel on the sides. If that happens, if it reaches a steady spread rate, this graph would flatten out. But it's because the fire line is accelerating up the drainage, you see a rising increase of heat release rate. An empirical model, such as the Ruddy Mell or Behave Plus, cannot account for this acceleration because it's a single fuel type, it's a single slope, it's a single input for the wind, and so you're going to get a single spread rate value because that's how it was designed. So this is an overview of current physics-based models in the US. And this footnote I have, number 1 footnote, is for a paper by Dominique Morvan, where he does talk about a wider range of models shown here. But what I'm going to focus on here are fire models in the US. And what I've done is, if you look at the left-hand column, which has the title scale, and you see there's bench scale, which is on the order of, it's an experiment you could do on your bench in a laboratory. So like a meter, on the order of a meter in size. And then you have, if you go down, laboratory scale, which may be 10 meters in size. And then finally field scale, hundreds or more meters in size. And then what I have in the second column are different predicted quantities at each of these scenarios that are important. And then I show in the rest of this table what the different models can, for each model, what can they provide in terms of at each scale and the predicted quantities at each scale. So WFDS was developed by NIST to look at structure fires and has been recently modified to handle fires and vegetation. So its history is such that it was developed to work at the lab scale or bench scale and lab scale all the way up and predict heat fluxes, heat release rate, mass loss rate, etc. All things important to understanding fire behavior. FireTech, which is a model from Los Alamos, has been designed to work at field scales. So that's why it shows up only in the field region here of this table. Dwarf Fire is a model focused on atmospheric physics and so does not have the fire physics captured. It's heavily approximated, but it can predict fire perimeter evolution, as I'm showing here in this table. And then FarSight, I think you're probably mostly familiar with, is a fire front propagation model, and that's so it can predict the fire perimeter. And then finally, we have WFDS level set, which is essentially equivalent to FarSight. And it and the physics-based portion of WFDS are in the same software package. And the point of that is so that we can compare a simple model to a more complex physics-based model to try to improve the simple model. This next slide shows it compares WFDS level set, which is the simple model, not the physics-based model, to FarSight. And this is a 1 kilometer by 1 kilometer domain. And these images in the top row are, as you go from left to right, you're going subsequently down in time, larger and larger times. And the blue square is an area where there is no fuel. And then you have a point ignition. And you can see the black is where you've burned out all the fuel. And then down below, and these images are the level set, the WFDS level set predictions. Down below, and it may be somewhat hard to see, are plotted the fire perimeter locations, fire front locations at different times from both FarSight, which is a lighter color curve, and the level set, which is the black curve. And you can see the agreement is very good. And then the second two graphs are showing the burned area, total burned area, and then just the fire perimeter, the length of the fire line from the two models. This is just to show that if we can test the level set model and find out how to improve that, then we can also use that information to improve farsight and other simple models. But there are limitations to farsight, and that's what the next couple slides show. Again, as I said before, there's this quasi-steady rate assumption for all of the models built off of Ruddy Mell, including farsight. So the top row here is showing something, this is all showing something very similar to the last slide, where you have a fire heading towards an area where there's no fuel, which is this yellowish square in the middle, 50 meters by 50 meters. And you have a spot ignition. The winds are fairly light here at 1 meter per second. And what's plotted in the upper row in the thicker green is the fire line from the physics-based simulation. That's the thicker green line. And then the thinner green line is the fire line from the level set simulation, which you can think of as being farsight. As the fire, so on the left hand, upper left hand, you can see they both agree. And what's happening is you do have an acceleration of the fire line, and that's built into the level set model based on the Australian empirical model. They account for a fire line acceleration based on the width of the fire, of the head fire. How long is the head fire? The shorter the head fire, the slower the spread rate. The larger the head fire, or the longer the head fire, the faster the spread rate. So you have an acceleration as the fire line grows, and that's accounted for in the model. Farsight would not automatically account for this. But I just want to mention that so that you know that's not an error here. It's being accounted for. As the fire line spreads past this fuel break, you see that the two fire perimeters from the two models begin to differ. And the bottom row shows why this is happening. In particular, if you look at the center of the bottom row, you see that you have air being drawn toward the fire from right to left, and then being redirected up to the flank fires, which then strengthens the flank fire and it spreads more rapidly. And that's why you see the physics-based fire line leaving the domain sooner than the level set fire line, because the level set can't account for this fire-atmosphere interaction that results from the breakup of the fire line. This is a similar case, but now we have in each square, we have mini squares, I should say, of no fuel. And those are what these, rows of squares you see on this plot are. Again, we have the physics-based and the level set shown here. The physics-based are the colored contours, they're thicker, and the level set are the red lines. Initially, you have a fire line across the whole domain. It's 300 meters long, and it progresses from left to right towards this landscape, which you can think of as an idealization of a community. So each of these boxes could be a house where you no longer have vegetative fuels. We're not going to let the house burn. We're just going to see what happens when you break up the fire line. This is also perhaps some kind of fuel treatment scenario, but of course it's just completely idealized. So what happens, the two models agree initially, and I'm putting numbers here to show you where they are. So 1 is the first location, 2 is the second location. By the time you get to 3, the level set is gone much further downwind than the physics-based. And what's happening here is, as I mentioned before, the longer the fire line is up to a certain point, past about 100 meters, it doesn't make much difference. But within 0 to 100 meters in fire line length, the longer the fire line length is, the faster the fire spreads. So when this 300 meter long fire line is broken up into smaller fire lines, the physics-based model accounts for the fact that it's a smaller fire line, and so you're spreading slower. The level set model cannot account for that, and so it keeps spreading at the rate of a 300 meter fire line. Now you could account for this kind of thing with a simple model, but the bookkeeping in a complex landscape with different fuel types and different fuel treatments would be extremely difficult. So from these kinds of investigations on the limitations of a simple fire line, the idea is to try to find out under what realistic conditions would the lack of, say, fire-atmosphere interaction here, that's what you're not accounting for, the lack of not, what is the importance of not accounting for that in the simple models? Are there some scenarios where you really should not use the model because those physics that you're missing are really important, and you'll get a prediction that really does not reflect reality in a way that's important to whatever you need to know from the model. Now I'm going to go through pretty quickly a range of application scenarios for the physics-based model, just to show largely the range at which you can apply this model. And the thing to remember here is that each scenario would require a different empirical model. But in this case, the same model can be used for each scenario. That's really the power of the physics-based models, because they capture the physical processes which exist in all these scenarios. They can be applied to all the scenarios with not much change at all in the model. The real changes that are needed are mostly related to what I mentioned before, that numerical error, because you're solving the equations on a grid. If you go to very large scales, you have to go to coarser grids because computers can't handle the demand that you're putting on them. If you're trying to resolve a fire with the same resolution that you're using at the lab scale, say a centimeter resolution, you can't do a centimeter resolution on a domain that's a kilometer by a kilometer. Computers are not capable of that. So some approximations have to be made, and there's some error because of the discretization I mentioned before. But otherwise, fundamentally, the model equations hold across all the scales. So starting at the small scale, this is a bench scale example. These are some experiments done by Jack Cohen and Mark Finney in Missoula, where they placed, as you see on the right-hand image here, they placed some sticks of fuel a certain distance from a radiant panel and measured the temperature. This particular case is a thermally thin fuel, so it's a millimeter in thickness. And on the right, you see a time history of the measurements as circles and the model as a line. And you see there's very good agreement. And what happens with this case is that the inflow, there's a balance of heat gain from radiation and heat loss from convection. And so you get a constant temperature. It doesn't heat up, it doesn't cool down predominantly either way. It stays constant because those two heat in and heat out are balancing. And the next slide shows on the left, you have in red here the net convection, the net radiation heat flux into the solid. So that's positive. And then on the bottom, you have convection, which is negative, because it's a loss of heat. It cools it down. It wants to cool it down. And the two added together are the net heat flux on the solid particle, and those balance out to zero. And that's why you reach that steady temperature. If we change things like made the clump much larger and embedded this particular piece of the material we're interested in the middle of a lot of other stuff, you're not going to have the convective heat losses, because you're going to have below this on the left, you have that red dot. That's our little fuel element. If you have a bunch of stuff below that blocking the flow, it's not going to cool down as well, and you're going to get a much more complicated picture, and you're going to get ignition. That was not considered in the lab, but the physics-based model, this is WFDS in this case, can handle all of that. These are now at a larger scale, still in the lab, and just showing from left to right different applications. On the far left, the burning of trees, individual trees. In the middle, some artificial fuel, rows of fuel on different slopes. And then on the far right, some laboratory experiments looking at the ignition of a crown fuel from a surface fuel below. So the far left and far right are more advanced. We have a paper on the left, we have a presentation on the right, and we're still looking. We're still working on the one in the middle. Going up further in scale, on the left you have grassland fires in Australia. In the middle are the International Crown Fire Modeling experiments. And then on the right is a focus on the smoke. So concentrations of smoke from, in this case, oil barrel drums being arranged in a circle and then burned. So we had measurements for those. Up further in scale, these are wind simulations. The image on the left is 8 kilometers on a side. And the way the model works is you send each of those subsquares in there, outlined by, I guess, kind of a purple color, to different processors on the computer. So that's 16 processors in this case. And what I'm showing down below to give you a feel for how expensive these things can be, if you assume that the grid cell size is 40 meters in the horizontal direction and 20 meters in the vertical, you can run this case and it's 10 times faster than real time. If you increase the vertical resolution so that the cells are only 10 meters, then it goes down to 3 times faster in real time. And then if you increase the resolution in the horizontal direction to make it twice the resolution, so 20, not 40 meters, it becomes 3 times slower than real time. So the question here is, what's a good enough resolution? And that does depend on what your application is. On the right, we have a much finer resolution case, and we're able to see that, and you probably can't see it, but the point of this simulation is to look at the different wind flow patterns through this trails community, which was burned in 2007, and to see if there are preferential corridors for the wind that could have carried firebrands through the community. In this community, at least 2/3 of the structures were ignited from firebrands. This is just showing another example of wind. And for here, we do have measurements. It was a forest canopy shown on the left, and on the right is the profile of the wind, with height. I won't go listen to the detail. It's just showing an example of another validation. And then for the wildland-urban interface, each row of this figure shows a case of different amounts of fuel loading. So the top row, the A1, A2, A3, are untreated, and it's based on actual loadings in the field, but untreated forest. And you have 2 structures in the middle there, kind of on the right-hand side. I hope you can see them. And then B is some marginal treatment of the fuels. And as you go from left to right on any row, you're going through time. And then C is a heavy fuel treatment. And you can see, of course, that the forest has been, the fuel loading has been reduced significantly, and the forest edge is much further removed from the structures. So with this simulation, you can get predictions of the heat flux on the buildings, not firebrand fluxes, but heat fluxes on the building, both radiant and convective. So and if you take that heat flux, and there's equations that have been developed by the Forest Service Wood Products Lab in Madison, you can take the heat flux and input it into this formula and find out if a wooden slab would ignite. You need the heat flux history to do this. So what I'm showing here on the left, if that quantity, when you put in the heat flux history, exceeds the red line, you will have ignition of a wooden slab, because that's what they used in the lab, a wooden slab. So for the no treatment scenario, you have an ignition. And for the treatment scenario that was the moderate treatment scenario, there was no ignition. Now, we don't know how well we are reproducing the heat fluxes for this fire because we don't have validation studies in the field that use this particular fuel loading. So that's an example, but this is an example of an application if we felt that the model was working well enough to apply this. So what is the status of physics-based models at this point? And again, I'm talking about models not focused on atmospheric physics, but more on the fire physics. The capability exists currently, as I've shown in the previous slides, for general but slower than real-time application. That means they're useful research tools, but they are not, it's not possible to use them operationally because of their cost. And it's not only their cost, but also it's pretty, it can be pretty complex in terms of input needs to run these things. We also need to have more validation of these models at the field scale and at the laboratory scale. There are significantly more measurements available at the laboratory scale, and so we've been focusing on that because of it. And we have reasonably good agreement, and I showed some examples in the previous slides with laboratory results. Recently, with the burn studies done in Eglin Air Force Base and some other places, we will have more field results for grass fuels, which is very good. But more is needed. And this just gives you an example of how the model has been applied to a laboratory experiment. These are the Catchpole experiments done in 1998 to improve the Ruddy Mell model. 290 simulations were made to compare to experimental results. And I'm showing on the left just a snapshot from on the top, from the side, and then the one below that from above of the case. This isn't a wind tunnel, so it will be subjected to the confinement effects I mentioned earlier. On the right is the usual kind of plot where on the left axis you have the modeled prediction of the rate of spread, and on the right you have the measured. So a perfect agreement would be all the points falling right on those, right on the line. And the circles are the WFDS model, and the X's are the empirical model from Catchpole. What happened, there's different ways of assessing how well the model worked. If you use an absolute mean error, it was within 29%, and 90% of the simulations were within 50% of the experiments. The Catchpole empirical model absolute mean error was 27%, so WFDS did as well in general, this is a general measure, as the Catchpole experiments. The Ruddy Mell model applied to this 53% absolute mean error, even though it's the same experimental configuration. So in general then, in a mean sense, the WFDS model worked just as well as the empirical model fitted to these points. In the individual sense, there's clearly some deviations, and that's often the most interest, why did they deviate? And so we're still looking at that. There were cases in the experiments where even for nearly the same conditions, you had widely different results. So there's some of that introduced in here. There's also some cases where model approximations were violated. And so we need to adjust the model so that, for example, for some of the thicker, deeper fuel beds, we were violating some of the model approximations. We need to change that and see if we improve the predictions. But if you can assess the model at the laboratory scale, because the equations are the same when you go to the field scale, as long as you feel you have sufficient resolution and sufficiently good input information, you can, with some confidence, take a model proven at the lab scale, a physics-based model at the lab scale, and move it into the field scale. That's why the laboratory measurements are important. And this is just showing a range of laboratory scale studies that are needed to improve these physics-based models. Momentum drag, radiant absorption, different thermal degradation models, as I mentioned early in the talk. They're not all representative of heat flux environments that exist in the field. Ignition is a very hard problem, which needs to be addressed, live versus dead. And then heat release rates of different vegetation, because the heat release rate is what drives the flow, fire-induced flow, and we have very little information on how different vegetations burn in terms of heat release rate. And then crown fire initiation. There are some studies on that, but that's a very important problem. Desirable field studies. There has been, like I mentioned before, there have been some field studies done recently, and the focus needs to be on the entire fire perimeter as well as local measurements. And in simple conditions, terrain and fuels first, along with heat flux measurements, firebrand measurements. There's very little very little information on firebrand generation of different, characterizing firebrand generation from different vegetation types, fuel break effectiveness or fuel treatment effectiveness in terms of changing the fire behavior and the fluxes of firebrands and heat fluxes, and then terrain and vegetation influence on wind flow, since those will also drive fire behavior. So most of this talk, I've looked at two different types of models, and both those types of models are important. The physics-based models I mentioned can be applied across, the same model can be applied across a large range of scales, and scenarios, whereas the empirical models, strictly speaking, are limited only to conditions consistent with their data set of origin. So, but the empirical models, or simple models, are very much needed because they're so much easier to use. So the point here is that we need a suite of models, and we need to use the more complex models, not to replace the simple models, but to improve them and to provide guidance on their limitations. And this is the last slide. As I mentioned, we need measurements because that's where the truth lies. But these measurements have to be done, in my opinion, with the goal of improving the overall modeling situation, not to produce another empirical model limited only to those environmental conditions. So that means that when an experiment is done, it should be done in the context of all the other empirical models as well as the physics-based models that are available, and how is it contributing to the gaps in the empirical models, and how is it contributing to validating and improving the physics-based models so that they can be taken to even other scenarios which are probably never going to be able, we will never be able to measure, such as those that result in very damaging fires. So obviously this means that experimentalists and modelers do need to work together under a broader context. And then finally, the main point of all of this is that whatever model you're using, when you provide that to a user, you need to also give information on what its limitations are over the range of likely scenarios for which the user will apply the model. And that can include, terrain scenarios, wind scenarios, vegetation scenarios, ignition versus flame, fire spread, etc. So that is the end of my talk. Thank you.
Thanks, Ruddy. So do people have questions? If you do, please use them in the chat room there. Anybody have questions? It was very interesting. I learned a lot, and I don't know anything about this stuff, so I enjoyed it. I don't see that anyone's typing, so Ruddy, I think you probably covered everything that people needed to know, so I really appreciate that.
I would like to think that it was all well understood, but I don't know. Because of my delivery. I'll take it as a compliment.
I think you should too. So just as a reminder, somebody is typing here. Corey Blankenship is typing. But just as a reminder, this will be hosted on our website, the Northwest Fire Science Consortium website, for viewing in the future. So Corey, thanks you. Very great webinar. I agree. And with that, Dave, okay, we'll just let people kind of go on here and type in a few comments. All right, do you see Dave's question there?
I do. What's the first best thing we can do in the next 5 years? I would say, and we're already working on this, as Dave knows, look at the models that are being used now and try to provide, in any way we can, information on what limitations those models may have, You know, so that when a user uses these things, they have some idea of whether the scenario they want to apply it to is something that should be applied to. And I'm saying that because we can do that now. The next thing would, of course, be to get more measurements. Many of these models are sufficiently advanced that we're waiting for measurements to evaluate and improve them.
So I have a question while Steve is typing. Why haven't the limitations been made clear up to this point for folks to use these?
I don't really know the answer to that. I'm guessing it's because people realized that these models were pretty coarse approximations and just dealt with it, and learned to kind of tune it to their specific needs. But with current problems, say in the WUI and in fuel treatments and smoke transport, these simpler models, basically the margin of error is decreased to the point where you have to know the limitations for your application. And also the simple models don't produce things like heat fluxes that are needed to answer questions related to structure ignition, etc. So I think it's just that, people just learn to deal with it.
So Steve has a question or comment.
Yeah, can you address the relative complexity between grass, brush, and woodland, etc.? Steve, if you mean in terms of modeling, like how does it, if you go across these different fuel types, how does it change the demands on the model? It doesn't with the physics-based models, because grass and brush and woodland are all treated the same in terms of how the fuels are represented and how they burn, dry out and burn. But the way it does become more complex is the measurements to validate the model, because you can't do complex fuels at basically realistic scales in the lab. But yet it's very hard to do repeated controlled experiments in the field. And this is why it's so important to have everybody working together, so that the parts that you can control and are also relevant to the field, but you can control them in the lab, you do in the lab, and you build up an expertise. And then you go to the field and you have to weigh the fact that you can't do repeatable experiments, you're not guaranteed, but you've learned enough through the lab and the modeling to really focus on scenarios in the field that will get you the best bang for the buck. So again, it really does come back to the measurements. You have just focused on grass in terms of the field. Yeah, that's because that's the only experiments that exist. We can simulate any of this stuff. As Marty knows, I see Marty's there. He knows we can simulate a forest, a shrubland, whatever. It's just we don't have the measurements to evaluate the model for those.
Any other questions for Ruddy? Well, thank you very much, Ruddy, and thank you all for attending, and I guess we'll see you next time.
Okay, thank you, Janine. Thank everyone else too.
Thanks.